Okay, so in the previous video, we have explored the first two units on the expectation and variance of a DRV, as well as looking at linear combinations of DRVs together to solve some problems. So now we will be looking at this unit now on the binomial distribution and its applications. And in fact, questions on the binomial distribution take up a lot of marks in exam questions on this topic of DRV, as well as the fact that they can be integrated into other topics like normal distribution, which is going to be chapter S3 that we explore later. Okay, so you need to know the characteristics of a random variable that can be well modeled by a binomial distribution. So a binomial distribution is one of the types of probability distribution that you are learning in your H2 syllabus, the other being the normal distribution that is the subject of the next chapter, chapter S3. Okay, so in this case, we are still dealing with the concept of a discrete random variable x that we have introduced earlier. So everything that we have taught you earlier still applies. Okay, now it is very important that you need to know these two characteristics here for a random variable to be well modeled by a binomial distribution. So um, in this case, you generate a binomial distribution through an experiment involving independent observations of a DRVX. Okay, so it is important to note that in this experiment, there are only two possible outcomes, success or failure. So in the case of tossing a biased die, like one we encountered in example 10, we can say that, oh, maybe a success is that uh, we hit a 6. Let's say this is a success and everything else is a failure. Or let's say we say that either this or this can be a success. Everything else is a failure. That's what I mean by there are only two outcomes, success or failure. And the probability of a success, which is denoted by this small letter p, is a constant. Okay, this is the first characteristic. And the second characteristic is that all the observations of x, x1, x2, etc. are all independent observations of our discrete random variable x. Now, these two that I've underlined in green are very, very important that you need to memorize the wording of. One is the idea of the probability being constant. Second is the idea of the observation of x being independent of each other. So a lot of questions, including you will see in your tutorial S2 and your assignment S2, if you look at things like your tutorial S2 question 9, question 10, assignment S2 question 1 as well, it starts assignment S2 question 1 as well, yes. The first part of the question is just a worded answer. States in context two assumptions needed for something to be well modeled by a binomial distribution. Okay, so you always need to state in context. So you can't just copy paste this wording. You need to paraphrase a bit in context. Okay, yeah, that's pretty much it. But these are marks that can be very, very easily gotten. Okay, so please don't skimp on them. Please don't neglect learning how to earn these kinds of marks. Okay, um, and you can get a binomial random variable, which is the outcome of a binomial distribution, and this BRV is obtained when you have independent observations of a DRV. So in this experiment, in addition to having only two outcomes, success and failure, the other characteristic of such an experiment is that you have a fixed number of trials that is denoted by n. Yeah, hang on. Yeah, I was just zooming out so you could see everything that I wrote. Okay, so let's just say let us make an, I don't know, pink n. Okay, so this is a fixed number of trials. So if n is a fixed number of trials, then the probability of obtaining x successes in n trials, which is px equals to x, which is the notation, px equals to x has the following formula that can be found in MF27 as well. Px equals to x is denoted by n choose x, and then p, which is the probability of success, power x, and then 1 minus p power n minus x. Okay, please note this formula. This is a very important formula. You don't need to memorize it because it's in MF27, but you would not want to quote this formula wrongly. Okay. Now, in this topic and also the next topic of normal distribution, there is a lot of GC pressing involved because a lot of these probability distributions are very complex in nature, and hence you need to use the computational power of your GC to compute them. Now, there are two GC functions that are used. Okay, one of them is known as binom PDF. PDF standing for probability distribution function. So I can't show you your GC. Actually, let me just pull up. Can I pull up a TI-84 plus CE online? Can I get one? It's a simulator. Okay. So let's see if this works, just to demonstrate to you the GC functions. Okay. Okay. Stop. Okay, so what you want to do is you are going to want to go to second, okay, second vast, so I get distribution, and then I'm going to want to go all the way down. So it's actually denoted by, I think, A and B over here. So if you scroll all the way down, you get binom PDF and binom CDF. So if you don't want to scroll and I just want to select binom PDF, I can just go to alpha A, and this is binom PDF. So you use binom PDF to evaluate Px equals to K. So binom PDF is basically just a way of calculating this formula, this box formula here for you, so you don't have to. Okay, so let's just say in this case I have let's say I want 10 trials. Okay, and let's say my constant probability of success is 0.2, and then x value is this value of small x. So let's say I want to find Px equals to 3. So in this case, I want to have an experiment where I have 10 trials, where the probability of success in each trial is 0.2, and I want to find the probability of 3 successes in 10 trials. So I press paste and it will give this function over here. And then I press enter. This is 0.201. So in this case, my notation of my binomial distribution, I realize I haven't introduced that now. You can denote a binomial distribution as follows. So if I want to say that x is a binomial random variable, I write it as follows. X is a binomial random variable with number of trials n and probability of success p. So we can see in this example that we have just evaluated on the TI-84 that let's say we have this example of x having n equals to 10 and probability of success is 0.2. Then by binom PDF function on the GC, Px is equals to, what do we evaluate again? X equals to 3. That is to say the probability of there being 3 successes in these 10 trials is 0.201. Now let's try to use the binom CDF function to evaluate Px is less than or equals to K. So let's say I want to find Px is less than or equals to 5. Okay, so in this case, I'm going to go second vast, and then we saw earlier that binom PDF is A, right? So binom CDF is B. So I can just go to alpha B to select binom CDF. CDF stands for cumulative distribution function. So once again, I have 10 trials. This is fixed. I have probability of success 0.2. And let's say I want to find x less than or equals to 5. So my value of small x is 5. And then I paste. And this is 0.994. So I have a 0.994 chance of there being less than 5 successes in 10 trials. Okay, unfortunately, this is the limit of your GC's computational power. You can only either find Px is equals to k or Px is less than k, where k is a constant. However, there are 6 cases that allow you to transform a given probability range into a form that is evaluatable by either binom PDF function or binom CDF function. Actually, all these 6 are evaluatable by binom CDF lah. So remember, binom CDF is always x less than or equals to only this inequality sign. This inequality sign cannot. This inequality sign cannot. This inequality sign also cannot. Only this inequality sign can be evaluated by binom CDF. So how can I transform this to a form that is evaluatable by binom CDF? I'm going to show you. Now there are 6 possible probabilities that the question may ask you to find. So once again, in everything that I'm about to write for you, K, A, and B are constants that are fixed by the question. So, first case. Now, why does this work? Because remember, this is a DRV, discrete random variable. K can only take on integer values. So, for example, if I want to find Px is less than 6, Px is less than 6, because if x is less than 6, then what's 1 less than 6? 5. Because it can only take on integer values, what? It cannot be anything between 5 and 6. So Px is less than 6, it just equals to Px less than or equals to 5. Or if you generalize it, x less than or equals to k minus 1. Okay, and because you remember the sum of probabilities is equals to 1, right? So if I want to find x more than k, then it's just the complement of this. It's just the complement of p x less than or equals to k. So it's just 1 minus p x less than or equals to k. Okay, third case. This is the other equal sign that binom CDF cannot evaluate for you, right? So how do you transform this? If you think about this, right, Px greater than or equals to k is just the complement of this first case above. Why? Because let's say k is 6, right? I want to find Px greater than or equals to 6. So this means I want to find P is, let's say in this case, the sample space S is as follows: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is just a hypothetical example for the purposes of showing you why all these properties are the case, okay? So if I want to, if let's say k is 6, I want to find x greater than or equals to 6, right? So I want to find x is equals to this, or this. So it's anything from here all the way to 10. Isn't this just the complement 1 minus this set? And Px less than or equals to 5 is just Px less than or equals to k minus 1. Okay. Now the last 3 cases over here are dealing with if it's in between 2 numbers. So I have 3 possible cases for it being in between 2 numbers. Sorry. One is this, one is this. And the last one is this. Okay, so understanding these three formulas takes quite a bit of intuition, but in any case, you will never ever be asked to prove this or derive any similar formulae in A-level H2 math. Okay, you just need to know them, and that's all. These are the only 6 cases that the syllabus can possibly give you for transforming. Okay, so if you understood the top 3, that's excellent. If not, take your time to understand slowly. But the bottom 3, I'm not going to explain it because it's really quite complicated. So you can just memorize essentially. But the more you use them, the more it's going to become intuitive, the less it's going to be pure memory work. Okay, so you need to know that. And you see in each of the cases, as I said, the point of transforming is I want to make it into a form that is evaluatable by this binom CDF, so that I basically want to transform everything to this inequality sign, because binom CDF can only evaluate this inequality sign. Okay, so let us try, for example, in our hypothetical example, let's say I want to find P is between 2, X is between 2 and 6 inclusive. Just an example lah. So that's going to be my 5th case over here. So this is going to be Px less than or equals to 6 minus Px less than or equals to 2. Actually, it can also be intuitive if I lay all the outcomes out on a line like this lah. So you see, right? If I want to find P is between 2 and 6 inclusive, this means I want to find the probability. Sorry. If I want to find probability that X is between 2 and 6 inclusive, this means that I want to find the probability that X is either 2, 3, 4, 5, or 6. So this is just the probability of X being less than 6, which is this entire set here, minus the probability that X is less than or equals to 2, which is this entire set here. So this entire green set minus this entire orange set gives you this set remaining, which is exactly what I want. Okay, no, I'm so sorry, this should be X less than or equals to 1 because it's A minus 1. So yeah, this orange set is just going to be this. So you see how if I have this green set minus this orange set, I just get this part in white here. And you can apply similar reasoning to the other 2 cases, this case and this case. Okay, so if I'm going to try to evaluate this on the GC, okay, let's say I still have this case where I have 10 fixed trials and 0.2 probability of success. So I'm going to just key in now. I'm going to go back to my TI-84 and I'm going to key in binom CDF X less than or equals to 6. So you see the TI-84 will actually save whatever you last inputted for you. So you don't need to re-input. At least these 2 on top, the trials and the P, you don't need to re-input if you are dealing with the same variable. Check that you've pasted the right thing. Okay, so I want to get this minus Px less than or equals to 1. So I apply binom CDF again, but this time I want less than or equals to 1. And I paste. So you see that this is going to be equals to 0.6232. Or, 0.62332. So you want to TSF is just 0.623. Okay? Yeah, you can try to use the logic with this green unit and this orange unit, similar logic to try and derive and convince yourself why this case and this case are true in your own time if you want to. Okay. Because we're short on time, I can't show you more examples for every single case. So I'm going to go on to the next important part, which is also the last part that I need to show you before you can go on and work on your tutorial S2 and assignment S2, which is on page 28 of your notes. Recurrence formula to find the mode of the binomial distribution. So this is actually also your tutorial S2 question 11A. 11A or 11 part 1? 11 part 1 of tutorial S2. Okay, so the mode of the binomial distribution can be found using the recurrence formula as follows. So if you look at Appendix B on page 28 of your notes, the recurrence formula for the binomial distribution is given as follows. And in tutorial S2 question 11 part 1, you are asked to prove this case. So I'm going to show you how to prove it now. I don't exactly like the proof that has been given to you on page 28, so I'm going to show you how I have proven it here. Okay, it's a bit more rigorous, but I really feel that the proof of page 28 really skips a lot of steps. Now, so obviously you start with the premise that x is a binomial random variable with n fixed trials and p probability of success. So actually I'm just going through your tutorial question now already. But yeah, I really don't like the proof that they have given you on page 28. So I'm just showing you my proof for this particular formula, okay? So first, let us look at the definition of px equals to k. So this is the probability of x of k successes in n trials. So I can write it out by this formula above, which by the way is in your MF27, that this is equals to, why is my thing like that? Okay, this is equals to n choose k plus 1, probability of k plus 1, and then 1 minus p, n minus k plus 1. So obviously if you expand the minus sign in, you can just write it as n minus k minus 1. Okay? Why are my straight lines not correcting? Wait, I'm sorry. Just let me try to restart my OneNote. So sorry about that. Okay, that should be better. Now, yeah, okay. On the bottom, x equals to, I just realized how ugly this is. X equals to k, right? So this is just going to be n choose k, pk, 1 minus p, n minus k. Now we can expand this using the definition of n choose r. So if we expand this using the factorial notation, you remember you learned in chapter S1 probability that for any n choose r, the definition of n choose r is as follows. In this case, r is k plus 1. So I have r factorial, k plus 1 factorial, and then n minus r factorial. So it's n minus k minus 1 factorial. So that's a bit small. Okay, and then I copy the rest over. And likewise, I can do the same on the bottom, on the denominator of the fraction, where I have n choose k, and I can expand n choose k using factorial notation. Expand it like that. K factorial n minus k factorial, and then copy it over. Okay, you with me so far? Okay, let's go on to the last bit of this proof, where this will lead us to the results that you see. I can actually write this giant fraction as the product of a few fractions. Because this fraction here was in the denominator, now that I'm bringing it up, I need to flip it, so it becomes as follows. And obviously these two can cancel, and then the rest, originally here I had p is equals to p power k plus 1 over pk. So p power k plus 1 is really just pk times p. Remember your basic laws of indices. And then on the bottom, it's just pk. So once again, this and this can cancel. Okay? And if you think about it, right, n minus k, I can also write it as n minus k minus 1 plus 1. So if I write it like that, right, then you'll see really what is, what is this? It's just n minus k minus 1 times this term again. So this and this can also cancel. Okay, I know that was a bit confusing, I'm so sorry, bear with me for a bit, but you get where all my cancellation is coming from, right? So now after cancelling quite a lot of things, I can rewrite neatly. And this is just going to be p over 1 minus p. So if I combine this entire fraction together, that is just going to be n minus k p, because all the factorials can also cancel out. So I will end up just having k plus 1 and 1 minus p. And that is how I prove the recurrence formula. Okay, so I hope I'm sorry, that was pretty long and convoluted, and there are probably a lot of things that a lot of questions that you still have. But hopefully, as you keep in mind these 6 cases, as you keep in mind how to evaluate binom PDF and binom CDF on your GC, and you also know the mean, the mode of the binomial distribution. I've just realized, I'm so sorry, I just realized I forgot to cover in this video the mean and the variance of the binomial distribution. So right before I leave you to go and do your tutorial S2, please be aware that this is in your MF27, that the mean of the binomial distribution is, that expected mean of the binomial distribution is just NP, and the variance of the binomial distribution is just NP1 minus P, where X is a binomial random variable. Okay, these two are in your MF27. This one is also in your MF27. So these 3 formulae don't need to memorize. Okay, I'm sorry if this consolidation video was a bit disorganized, but I hope you've learned something and you can go on to do your tutorial S2. Also, all the best on that.